Hello and welcome to Empowered Learning. This is the third video in the definition of derivative video series. And so in the first two videos, what we talked about was the concept of a derivative in terms of the limit of the difference quotient. And we saw using an empirical example of how the limit of, let's say, the slopes of secant lines actually turned into the slope of a tangent line. In the second video, once we got that concept crystallized, we did several examples of where we were trying to find the equation of the tangent line that went along with the derivative of the function at a particular x value or at a particular point. And so one of the connections that we made was that the slope of the tangent line of a line is the same as the derivative of a particular function at the particular x coordinate for where that point is on the graph. And we also realized that the slope of the tangent line characterized instantaneous rate of change, whereas the slope of the secant line, which is another way of writing our difference quotient, which is another way of writing the slope of a line, was what we call average rate of change. And so now we're at a point to where we want to look at finding out what will be the slope of the tangent line for an assortment or various points on the graph of a function instead of just looking at it at a single point. And so in looking at it that way, what we come to find out is that we can actually find a formula for the derivative of a function for any x value that's in its domain, provided that we can actually take the derivative of that particular function at that particular x value. And so you'll see in the video that I'll prepare, that's called differentiability, you'll see there are instances where we can take the derivative of a function in the x value, and there are places where we cannot take the derivative of a function at a particular x value. And we'll illuminate those things at that time. But for right now, we just want to sort of work our way into being able to figure out, well, how do we find out a formula for the derivative of a function at several different x values instead of just at one? And so at the beginning of these notes here, you see that I say, recall that f prime of a, which means the derivative of the function f at a particular x value a, is the limit of the difference quotient. And I give it to you in one form where the x is a, and that is a specific value of x that we're looking at. And so in this form here, what we're saying again is that we want this point a, f of a, and we want the other point that we're looking at, a plus h, f of a plus h. The slopes, the slope of the line that goes through these 2 points, as the a and the a plus h gets closer and closer to one another, meaning when h approaches 0, ends up being the slope of the tangent line. Okay, and here we just express that in a different way, where we have the point a, f of a as one of those points, and x, f of x as another one of those points. Okay, so from the previous 2 videos, this is what we talked about, and we said that this is the definition of a derivative, which is slope of the tangent line, instantaneous rate of change of a function at some point, a, f of a. If x is allowed to be any real number in the domain of f of x, then we can come up with a function f prime of x that will track the instantaneous rate of change of f of x for any x value that's in its domain. And of course, there are some exceptions to that, but we'll talk about those later. And so my point is that if now we replace what we had here as a and a here with just an arbitrary x value, then what we can actually come up with is the formula for the derivative of a function at several x values. Or put another way, we have a formula tracking the slopes of the tangent lines of a given function for several values of x. And so now that we can come up with a function that tracks instantaneous rate of change of f of x, we can use these functions to track instantaneous rate of change in general instead of having to do it at every single point that we're considering. So the point I'm trying to make there is, if you looked at the previous video, you saw that we were just trying to find out the slope of the tangent line at a single point. But by coming up with these formulas, we can come up with the slope of a tangent line for several points, and it won't take much effort to do it. So let's look at our first example here. And so we want to consider the function f of t, which is negative 2t squared plus 8t. And we want to find out what is the derivative of the function using the definition of a derivative. All right, so the first thing that I want to do is I want to make sure that this gets fixed here. So this says f prime of x, but it should actually be f of t. So I'm going to go ahead and change that now. All right, so now that we have that fixed, the first thing that we want to realize here is what it is that we're actually trying to do. So we're trying to take the derivative of the function t, which we're going to say will be the limit as h approaches 0 of the difference quotient, and we will write the difference quotient this way. Okay. And this says f of t plus h minus f of t, all that divided by h in here. So I'm going to try to make that look a little better before we get started there. So it's a little bit more readable. All right, and so the first thing that we want to do is really just figure out what that difference quotient is going to look like. And so I'm going to start off by doing this in pieces. Depending upon where you're studying this, they either do it all at once or they do it in like a 3 or 4 step process. For this problem, I'm going to do it in a 4-step process, but as we go through other examples, I'll just kind of consolidate everything. So first thing that we need to find out, well, what is f of t plus h? Okay, so this basically says wherever we have t here, we're going to now replace that with t plus h. So we have negative 2 times t plus h squared plus 8 times t plus h. And so here we need to FOIL out the t plus h. So that's like t plus h times t plus h. And when we FOIL that out, we get t squared plus 2th plus h squared. And then that'll be plus, now we distribute 8t plus 8h. And so now from there, all we need to do is distribute the 2 to all 3 terms here. So that'll be negative 2t squared minus 4th minus 2h squared plus 8t plus 8h. And so the next step now is we need to subtract what we see here from f of t. So we have f of t plus h minus f of t. So now we just write everything that we came up with in the previous step. And now we're going to subtract all of f of t. And of course, f of t is negative 2t squared plus 8t. And notice I put that all in parentheses. So from there, what we're going to see is every term that does not have an h in it will eventually cancel out with another term. And so here you see that we distributed the negative to both terms there, which changed the signs of both of these terms. And so here we see that we have a negative 2t squared, and that should cancel with a positive 2t squared. So that cancels to 0. This term has an h in it, we leave it alone. This term has an h in it, we leave it alone. This is plus 8t, so we have a minus 8t to go along with it. So that cancels to 0. And so what we have left are just the terms that have an h in it. Okay? So now that we have that, we can now do the last part, which would be we need to figure out what all this is going to be divided by h. Of course, we have what we have here in the previous step in the numerator, and just divide that by h. And so now it depends on how you want to do it. You can separate this into 3 separate fractions and then reduce the h's, or you can factor out the h and then reduce. And so I'm going to choose to do the latter. So I'm going to factor out an h out of each term. And then here I see that those h's reduce to 1. And all I have left is a negative 4t minus 2h plus 8. And so now, if I wanted to find out what is the derivative of the function f, it's the limit as h approaches 0 of the difference quotient. But now our difference quotient is going to look like this. And of course, to the limit operator, h is the variable. And of course, this looks like a polynomial to this, a polynomial of degree 1 to be exact. So in looking at it that way, we will just evaluate this expression at 0. And we see we just get a negative 4t plus 8. And so this would be the actual formula for the derivative, or the slopes of the tangent lines, for our original function here. And let's go back. Our original function here, which was negative 2t squared plus 8t. And so with that formula of 4t, negative 4t plus 8, we can track the slopes of the tangent lines at any given value of t on that function. So now what we want to do is state the domain of the function itself and its derivative. So of course, the function itself was negative 2t squared plus 8t. This is a polynomial of degree 2, or a quadratic. So of course, its domain is going to be all real numbers. The derivative is a line. And of course, the domain for any line is also all real numbers. So that one was pretty easy. So now what we want to do is sketch a graph of both of these functions here, the original function and the derivative, and see how this will actually look on the same plane. Okay, so we're going to go ahead and do that now. All right, so let us go ahead and write down these functions again. All right, so our f of t is just negative 2t squared plus 8t. And we know that we can factor out the greatest common factor, which would be a negative 2t. And what would be left is t minus 4. And so, of course, that lets us know, if we were drawing this, that we have an x-intercept at 0 and an x-intercept at 4. And our parabola is going to be opening down. We can also go ahead and find out what our vertex is. H is just minus b over 2a, where our a here is a negative 2, our b is an 8, c is 0. So we have negative 8 divided by 2 times a negative 2. A negative times a negative is a positive. 2 times 2 is 4. And 8 divided by 4 is 2. Corresponding value k, we'll just plug in 2 into that function. This should be easy to do. And so that'll be negative 8 plus 16. So that'll be positive 8. So we know we have a parabola that opens down. We have x-intercepts at 0, 0, and at 1, 2, 3, 4 here. We know that at 2, 8, we have a vertex opens down. So this graph will look something like this. So now what we need to do is draw our line. So our line is the derivative, which is negative 4t plus 8. So we know here y-intercept is at 8. And if we want to find another point on the graph, we can just use the slope. So we can go down 4 units into the right one. So 1, 2, 3, 4, 1 unit. Let's see, 1, 2, 3, 4, 1 unit. 1, 2, 3, 4, 1 unit. 1, 2, 3, 4, 1 unit. And 1. Yeah, so that should be enough. So now we can just draw that line. Of course, it's not perfect, but you see the idea here. All right, so in looking at this, one of the things I want you to realize here is how the actual derivative is letting you know information about the original function. And if you notice, first thing is at x equals 2 here. Oh, let's erase that. So at x equals 2, do you see how this is the x-intercept for that, but this also goes with the same place where this graph has a maximum. Okay, and so one of the interpretations for the derivative of a function is to know when is the graph of a function increasing and when it is decreasing. So for each point on the graph of the original function, if we did the slopes of the tangent line for each of these points as we went up, what we would see is that the slopes of those tangent lines would be positive, which means that the graph is increasing for that particular x value. And so if you notice here, the graph is increasing for the original function for all values of t that are less than 2. And our graph is decreasing for all values of t that is greater than 2. And that corresponds to, with the derivative, the graph of the derivative being above the x-axis for all values of x that are less than 2, and being below the x-axis for all values of x that are greater than 2. So point there is whenever the graph of the derivative of a function is above the x-axis, what that is communicating about the original function was that that original function was increasing. And when the graph of the derivative is below the x-axis, what that is communicating is that the original graph was decreasing. And of course, the place where the graph goes from either being above the x-axis to below the x-axis as far as the derivative is concerned, that place is where you either have a maximum or a minimum point on your graph. And in this case, since we have a situation here where the graph was above the x-axis and then below, then we know that for the original function, that was a maximum, or what we call a local maximum there. Okay? And so that's what one of the other things that the derivative of a particular function actually tries to communicate to us. And that's one of the reasons why I wanted you to see the graph of both of them together. Now, the last thing I want to mention here is, do you notice how for the original function, if we were tracking the slopes of the tangent lines, the slopes of the tangent lines are positive, but they get less and less and less positive because, of course, right here at x equals 2, we have what's called a horizontal tangent line there. And so, of course, to make that happen, the slopes of the tangent line had to get positive, but less positive until it got to a point where the slopes of the tangent line are 0. And then on this side, the slopes of the tangent line get negative and more negative. Well, the graph of our derivative is also communicating that to us. We see that way up here, the slopes of the tangent line are really positive because that's what the derivative means. It's tracking the slopes of the tangent line. So when it's up here, that means that the slopes of the tangent lines are really, really positive, but they get less and less and less and less and less positive till they hit 0. And then they start to get negative, 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 and more negative. Okay? So as we see, the graph of the derivative of a function actually gives us some insight onto how the original function actually looks. All right, so looking at our next example here, we kind of want to take a different route, and now we want to find the equations of all lines having a slope of -1 that are tangent to the curve 4 divided by x minus 6. So first thing that we want to do, it's not necessary to do this for this problem, but I know I like to do these things just to kind of give me a visual interpretation of what's going on before I start working on a problem. Let's actually sketch a graph of 4 divided by x minus 6 and see what this is all about. So if we start off by sketching a graph of this, we know that the parent function for 4 divided by x minus 6 is just 1 over x. And so 1 over x in general is just a function that kind of looks like this. And so, of course, the minus 6 here just means that the vertical asymptote is now at x equals 6 instead of x equals 0. And this 4 here is just a vertical stretch. So if we just sketch a quick graph of what that looks like, this is x-axis, y-axis, and we have our vertical asymptote here at x equals 6. In general, this graph would look something like this. And of course, we have a horizontal asymptote at y equals 0. Now, what we're looking for here is to figure out the equations of all the lines that have a slope of -1 that are tangent to this curve. So what we're really asking for is we have some points here that we can identify on the graph to where if we were to draw the tangent lines, we would see that the slope of those tangent lines would be -1. And so what I'm going to do now is go ahead and draw what that might look like. And so that'll give us sort of an idea on how to move forward in this problem. Okay, so what I've done is I've actually created 2 points here, which is this point and this point, and I've kind of sketched in a short tangent line. And so if you notice, both of these lines here have a negative slope. And so what we're saying here is that we're imagining that these 2 lines have a slope of -1 here. So that's actually what we're trying to find. Now, we know that in order to find the slope of the tangent lines at a particular point, we can find the derivative of the function. So what we want to do now is work on actually finding what is going to be the derivative of the function 4 divided by x minus 6. And then once we come up with that formula, we can figure out when the derivative is actually going to equal to -1. So in other words, find the formula for the derivative and then set that particular function equal to -1 and figure out the corresponding values of x. And then that will give us the x value locations for where we actually have these points that we're illuminating here and here. And then from that, we can find the corresponding y values and then find the equation of the tangent lines. All right, so let's go ahead and get started with actually finding out the derivative of this function first. All right, so the first thing that we want to do is just make sure that we let this equal to function f of x. And so we know that f prime of x will be the limit as x approaches, sorry, not x, h approaches 0. So let's fix that. As h approaches 0 of the difference quotient. And remember that the difference quotient is just a fancy way of expressing the slope of a line, or in particular the slope of a secant line. Let's go ahead and figure out what that difference quotient is going to look like. So here we know that everywhere where we see x here in the first term, for this function, we're going to replace it with x plus h. So here this time I'm not going to do the four-step process. I'm just going to do everything all together at once. So we have that minus f of x, which is just 4 divided by x minus 6. And then all of that divided by h. And let me make sure that we recognize that that is 6. Okay. So now, of course, algebraically speaking, we need to work on this to make this look the way that we want it to. So just to make this look a little bit easier to deal with here, I'm going to do this. And all that will be divided by h. So here we see that our LCD for this will be x minus 6 plus h times x minus 6. So if we want to form our numerator into one quotient here, then we need to make equivalent fractions. So for this first fraction here, we need to multiply the numerator and denominator by x minus 6. So we'll go ahead and do that. And for the next one here, this will be, we need to multiply this by x minus 6 plus h. So we'll have the 4 here, and this will be x minus 6, like that, plus h, close. And then all of that will be over x minus 6 times x minus 6 plus h. And then, of course, all that will be divided by h. So then from there, we'll simplify what we can in the numerator's numerator. And we know here that because of complex fraction division, the h will just move up. So if we do this, this will be 4x minus 24 minus 4x plus 24 minus 4h. And all that will be divided by h times x minus 6 times x minus 6 plus h. And if you notice here in the numerator, every term that does not have an h in it will cancel to 0 with something else that you see. So 4x and negative 4x cancel, negative 24 and 24 cancel to 0. And all we have left is the negative 4h divided by h times x minus 6 times x minus 6 plus h. And of course, these h's here reduce to 1. And all we have left is the negative 4 divided by x minus 6 times x minus 6 plus h. And so now we have a way to express the difference quotient in a way that will actually allow us to be able to evaluate the limit. So now we come here and say, therefore, the derivative of the function f of x now is the limit as h approaches 0 of negative 4 divided by x minus 6 times x minus 6 plus h. And of course, due to all of our limit laws, and the direct substitution property, we know that we can just plug in 0 here for h. So in doing that, we end up with negative 4 divided by x minus 6 quantity squared. And so this particular function here will model or track the slopes of the tangent lines for every value of x that is in the domain of our original function 4 divided by x minus 6. So now what we need to do here is note that we're trying to find out the equations of the tangent lines where the slope of the tangent line for each of these would be 1. So here we know that, of course, this function, another way to look at this is as the slope of the tangent line. And so what we need to do is set our derivative function here equal to negative 1 and then solve for x. And that'll let us know the x values for where we have those tangent lines that have a slope of negative 1. Okay, so I've made some room to go ahead and do these calculations. Therefore, we know that negative 4 divided by x minus 6 quantity squared equals negative 1. And of course, we just need to solve that for x. So if we multiply both sides of this equation by a negative 1, then we'll see that it becomes positive. Then here we can just put this over 1 and cross multiply. So that'll be 4 equals x minus 6 quantity squared. And so from here, if we take the principal root of both sides, we'll have plus or minus square root of 4 is equal to x minus 6. And then of course, we know from there that square root of 4 is just 2. And if we add 6 to both sides, what we will end up getting is a 6 plus or minus 2 equals x. And so that implies that x is either equal to 4 or it is equal to 8. So we know that when x is equal to 4 or when x is equal to 8, the slopes of the tangent lines at that particular point is negative 1. So remember, the original thing that we were trying to do is find the equations of the tangent lines. So now that we have the corresponding x values for those points, we can now figure out what the corresponding y values are. So from here, we know that our original function again was this. So this implies that f of 4 is going to be 4 divided by 4 minus 6, which gives us 4 divided by negative 2, which is a negative 2. And we know f of 8 will be 4 divided by 8 minus 6, which is just 4 divided by 2, which is 2. So, and all of this implies that we have the points 4, negative 2, and 8, 2 on the graph of f of x. And so now from there we can use these points to be able to find the equations of the lines for the points that have a slope of -1. Alright, so let's go ahead and find out the equation of the line for the first one. So let's say at x equals 4, we know that our slope is going to be -1, and the point that we are going to use is the point 4, -2. And so I'll use the point slope form of an equation of a line this time to find it. Where this is our x1 and y1. So we have y minus y1. Slope is -1, and x1 is 4. So this gives us y plus 2 minus x plus 4. And we subtract 2 from both sides. Then we have y equals -x plus 2. So that would be one of the equations of the tangent lines. The other one is when x is equal to 8. So, of course, this time our slope is still -1, but our point now is 8, 2. And I'll use the slope-intercept form to find the equation of a line this time. And so I'm just switching it up so you can see it done in different ways. We'll call this our x, call that our y. So our y is 2, our slope is -1, our x is 8. We have b is the y-intercept, which we're going to find. So -1 times 8 is a -8. And so if we add 8 to both sides, we see that we have 10 is equal to b. So therefore, second equation is a -x plus 10. So those are our two equations of tangent lines to the corresponding points that we were talking about. And so now what I'll do is go back up to the beginning of the problem and actually draw these lines and show you how the way that these lines look actually makes sense as far as the original graph that we had drawn in the beginning of the problem. All right, so going back to the original problem, if we look at our first line, remember our first line was y is equal to -x plus 2, and so that would be this line here. So if we came down, we would actually draw the line. You'll see that that's how it would look. And of course, here it makes sense that the y-intercept for that line would be 2. For the second one, if we come here and draw the line, see that it's way up here. And of course, it makes sense that here the y-intercept for that line would be 10. And of course, both are parallel to one another because they have the same slope. And we see that everything works out with it. All right, so to conclude this video, I want to talk about the different type of derivative notations that we use. And so what you've been seeing up to this point is what we call prime notation. Okay, and so we also use a notation called Linus notation. And so this is the basic general differentiation operator. And so all that I'm trying to say here is that sometimes you'll see it written this way and other times you'll see it written this way. And they both mean the same thing. Okay? So here we see that if we see something that says f prime of x, which is the same as y prime, which is the same as dy over dx, which is the same as df over dx. And of course, sometimes you may see it written separately like this. As you study higher mathematics, you'll actually see this operator too. And when you start to study mathematics where you're dealing with more than just one variable, like multivariable calculus, you'll see that we're trying to take the derivative here with respect to x. And so they just have these different ways of being able to express that. So these symbols, the d and the little d over little x, are called differentiation operators. And the reason that they're that because writing these operations will indicate that you're doing a certain operation of differentiation. So what do I mean by that? All right, so just like we have the operation addition and subtraction and multiplication and division. Of course, we learned those things a long time ago, but there's a lot that goes into actually being able to say that, for instance, 2 plus 3 is 5. So it doesn't seem like it, but there are a lot of things that we had to build up on mathematically to be able to say that. So that operation of plus or addition, you intuitively know that you need two things in it to make that happen. And then you have to know what the concept of 2 is, what the concept of 3 is, and what the concept of 5 is in relation to 2 and 3. So, of course, there's a lot of stuff that goes into that. Now, the point I'm trying to make is on a higher level with the differentiation operator, if we look at the summation operator or the product operator. So these are other operators that we use to imply that we're doing certain things, and it's already implied what we're doing, but we don't want to repeat that explicitly every single time. Okay, so for instance, the summation operator, you're saying that whatever expression that you have after you write the summation operator, you want to be able to add that by doing iterations of, in this instance, k. So k acts like your variable, and you have this particular expression, and you want to plug in 0 for k the first time, then 1 for k the second time, and then 2 for k the third time. And all this stuff is implied when you say that. When we use this differentiation operator here, or even say this, what we are implying is that we want to take the limit of the difference quotient, which means we first of all have to understand what a difference quotient is. After that, we have to understand what a limit is, and then understand what does it mean when we're taking the limit of a difference quotient. Or put another way, what does it mean when we are studying the behavior of secant lines as the points in between those 2 points that form the secant lines, horizontally speaking, get closer and closer to 0 to eventually form what we call a tangent line. So you see there's a lot of stuff buried into that, okay? And so, again, this particular notation is called Leibniz notation, named in honor of Gottfried Wilhelm Leibniz, a German philosopher and mathematician from the 17th century. Okay, and so the dy and the dx that you see, what they're really there for is to say, all right, we want to represent theoretically the smallest incremental change in the y value and smallest incremental change in the x value. And if we do the average rate of change of smallest possible change in y value over smallest possible change in x value, that is essentially what we are interpreting as derivative or instantaneous rate of change. So that's why we use those operators. Now, if we use these operators and say that we want to evaluate the derivative at some specific value a, then of course these are all the different ways that we would do that. So here we could say dy over dx and just put a line and say as x is equal to a, or some people do it with the little bracket. If we were doing it in prime notation, we would just substitute in whatever that value is for x there. Okay. And if we wanted to write our difference quotient in the incremental format, then of course we could also express the derivative as the limit of the change in y over change in x as x2 goes to x1, of course, or we can say as x1 goes to x2 depending upon what you want the variable to be. But at the end of the day, we know that change in y over change in x is just this, and so we can also express it as the difference in between x2 and x1 will be approaching 0. So now let's talk about higher derivatives. So we'll see at times that we'll need to be able to take a derivative of a derivative, and if you're studying calculus, at least the first year of it, you'll see that we have an interpretation of the second derivative of a function and you'll learn that this ends up being, it tells the concavity of the graph of the original function. So if we're looking at in terms of, let's say, distance or displacement, if we take the derivative of, let's say, of displacement, that's going to give us velocity. And so the derivative of velocity will be acceleration. So the second derivative of a position or displacement function will be acceleration. And so that's some of the ways that we can use second derivatives. So my point here is that, of course, if we use that notation, we have the f double prime or y double prime. It's also written this way as well. And of course, if we split it out, we know that if we're going to take the derivative of the function's derivative, then it could be written this way. Now, if we want to extend this idea to, let's say, taking a third derivative, then we could use f triple prime or y triple prime. We could take the derivative in Linus notation of the second derivative that's already in Linus notation, or we can write it out all explicitly, or we could write it this way. Okay. Now, if we want to go higher in derivatives, it's customary for us not to use the prime notation for anything higher than a third derivative. So for instance, let's say if I wanted to take the 25th derivative of some function, we're not going to do f and then 25 prime signs before we write the x there. So that would be a little long. So what we do beyond that is we just write a number here. So that's what I'm going to show here. So if we want to take the fourth derivative or the fifth derivative or the eighth derivative, this is what it would look like. Okay. And so in general here, we know that we can write our derivatives, the notation for it, in these following ways. And so in doing this, we want to make sure that we know that whenever we're trying to use this notation, that the n is just a natural number. So we'll have 1, 2, 3, 4, 5, or 6. And of course, for values of n that are 1, 2, and 3, we just use the prime marks if we're using the prime notation. And for the Linus notation, if your n is just 1, meaning the first derivative, we don't write that. And so this concludes the third video in the definition of derivative series. So I hope this helped, and if you have any questions on anything, just please comment, and I'll respond to you as soon as possible. Take care.